So today we're going to tackle some more calculations that have to deal with distillation columns and separations in general. So first, I want to define something known as the relative volatility. So if we have a relative volatility of two components, component 1 and component 2, that is equal to a measure of volatility, a measure of the vapor-liquid equilibrium that is described, so this K, or I guess we go K sub I, is described as the mole fraction of this component in the vapor phase over the mole fraction of this component in the liquid phase. So if we have this K1 over K2, that's simply Y1 over X1 times X2 over Y2, which is the reciprocal over here, the 1 over K2. So we're just multiplying by the reciprocal. Furthermore, we know that the sum of any components xi is equal to 1. So for example, x1 plus x2 in our binary mixture should equal 1. Given that information, we can put everything in terms of a singular component. So our goal here is to define the vapor mole fraction of this more volatile component, which would be our first component by definition. We are trying to get this vapor phase mole component in terms of the liquid phase mole or the liquid phase mole fraction of that component and the relative volatility. So we can write out something like, so 1 minus x1 equals x2, and then all this over, it's a really bad line. Why is it not? There we go. Times x1 times 1 minus y1, because this same postulate also exists for the vapor phase as well. So I'm going to get rid of all this so I have a bit more room to reorganize. So essentially now what we have is this relative volatility and this expression here in terms of the vapor phase mole fraction and the liquid phase mole fraction of component 1, the more volatile component. So now I'm going to multiply this denominator over to this side. So we have now something alpha, so x1 minus x1 y1 is equal to y1 minus x1 y1. Now our goal here is to isolate this y1 term, so that's just going to take a bit of manipulation here. So I can start by getting all my y terms on one side. So let's do ax minus xy. I'm going to drop the subscript so I don't have to keep doing that, but we know that by this derivation, this is for our more volatile component. So alpha xy here, alpha xy is equal to y1 minus x1 y1. So just xy here. Let's bring this over to this side. So we get now alpha x equals y minus xy plus alpha xy. We'll take our y out. So y1 minus x plus alpha x. So finally what we get is that our y, our vapor phase mole fraction of this more volatile component, is equal to the relative volatility times our vapor phase mole fraction over 1 minus vapor phase mole fraction plus relative volatility times our vapor phase mole fraction. So this, what we have here now, that was bad. What we have here is our vapor phase mole fraction in terms of our liquid phase mole fraction and our relative volatility. So the next thing I want to do here, so we'll keep this in our back pocket. The next thing that I want to do here is, I think my shape is off. There we go. Now it should work. So we have a term that is known as the boil-up ratio. And that boil-up ratio, well, maybe let's just start here. That boil-up ratio is defined, so V sub B is defined as this vapor flow rate for our stripping section of our distillation column over the flow rate of our bottoms product. So the boil-up ratio is a measure of how much of our bottoms product, so the product that comes out of the bottom of a distillation column, how much of that product are we reboiling and using as vapor to conduct our distillation process. So if I were to draw that out, so let's say we have a feed stage here. Right here. So if we have some feed coming in, so this is our F, what leaves from our feeding stage is we have our vapor that is used in our rectifying section, and we also have entering is our vapor flow rate from our stripping section. So if we did a mass balance for this section of our column, we get, so what's entering is our V bar, right? And then we also have our, maybe I'll write it this way. So first I'll go what's exiting. So our vapor for our rectifying section is what's exiting, equal to our feed times 1 minus Q, because this Q is representative of our feed quality, which is a measure of what is our liquid mole ratio. So this Q stands for whatever is liquid. 1 minus the liquid is going to be our vapor feed. So that intuitively makes sense. Plus V bar, because these are the two things that are entering. Now, if you look at our equation for our boil-up ratio, this bottoms here is something that we should know. This vapor is something that we are wanting to get in terms of our reflux ratio, our distillate flow rate, and one other thing, our Q. So let's go ahead and do that. So now, essentially we have this V bar is equal to our feed, 1 minus Q, minus V. And we know that from an overall mass balance of our distillation column towards the top end, so now we're looking at our total condenser, our vapor is what is exiting our, our vapor is what's entering our total condenser, and what's leaving is our liquid reflux and our distillate. So that looks something like this. So this now can go here, and we can do that like this. So V bar equal to feed 1 minus Q minus L minus D. Now the last manipulation we're going to do here has to deal with now our reflux ratio. So similar to our boil-up ratio, our reflux ratio is a measure of, we have our total condenser and we have our distillate exiting. How much of that distillate are we then recycling to use as liquid for our rectifying section? So that is equal to whatever liquid we're using for our rectification over our distillate product. So our L ends up being equal to RD. So one final manipulation equal to our feed 1 minus Q minus RD minus D. And we can simplify that by conjoining these like terms. So now V bar equal to 1 minus Q minus, if we take a, if we take a minus D out, no, let's just do this, minus D R plus 1, right? I believe that should be right, because if we take out a D, we get a R minus 1. So actually, no, this should be, which we can rewrite to make this make a little bit more sense. If we take out that minus here, put it there, and then rearrange this, R plus 1 D minus F 1 minus Q. And now we have this, well, we're not actually done yet. Last thing to do is to put this, this equation we've just derived into our boil-up ratio. So now our boil-up ratio, let me use white. So now boil-up ratio is equal to R plus 1 times D minus feed 1 minus Q over our bottom's flow rate. So now we have this boil-up ratio in terms of our reflux ratio, our distillate feed rate, or sorry, our distillate flow rate, our feed flow rate. This 1 minus Q is indicative of our feed quality. So this is the vapor feed rate, and this is our bottom's flow rate. Now, something else I'm interested in is what is the intersection of my stripping operating line in the upper edge of our XY diagram, which is to say that when our Y is equal to 1, what is our X equal to in our stripping section? Well, that can be easily calculated using the equation that we had previously derived for the stripping operating line, which is that Y is equal to VB plus 1 over VB times our liquid composition minus our composition of the bottoms over VB. So in this case scenario, our vapor mole fraction is equal to 1. So in this case, rewrite this out. Minus XB over VB. In this case, what we want to solve for is this X. So let's go ahead and do that. So our first step, we're going to add this XB over VB over to the other side. Over VB. VB plus 1 over VB times X. And we know that this 1 over XB, if we do just the common denominator and add 1 to that, we get VB plus XB over VB. That's essentially the same as this. So what we can do is we'll multiply this VB over to this side, which will cancel out with the bottom, but I'll just write this out long form first. So VB times VB plus XB over this denominator, VB plus 1, whoa there, equals X. And so this top and this bottom cancel out. And what we finally are left with is this nice equation for our liquid composition, which is our boil-up ratio plus our composition of the bottoms over our boil-up ratio plus 1. That is the calculation for our liquid mole fraction for when y is equal to 1. So very quickly, now that we have all this, the last thing that we can kind of provide some insight into is, well, if we have a McCabe-Thiele diagram, we have this characteristic of the x equals y line that looks like a straight line, hopefully. We have this characteristic x equals y. We have our vapor-liquid equilibrium curve. We have our rectifying down here somewhere, or sorry, stripping down here somewhere. And this is a line that goes up maybe like here. This is all just very representative, not necessarily to scale, but it'll help me show you that there is a common intercepting point here. And this is actually, in fact, shared with our Q line too. So this point right here is the intersection of all three operating lines on a McCabe-Thiele diagram. So the way we can calculate that is just using any two equations and finding that intercept point. So I'll choose my two favorite, which is the Q. So that looks like this. So y equals q over 1 minus q. Actually, I'll write it like this, just so it makes a bit more sense in my head, actually, in this way. So q over minus, so minus q over q minus 1 times x, and then we also minus 1 over q minus 1 times z, which is our feed. That looks right, because now if x equals z, it's q minus 1. Yeah, this looks right. So q over q minus 1 minus 1 over q minus 1, if x is equal to z, like if say this was z, then it would be q minus 1 over q minus 1 times z, and then y equals z. Makes sense. And I'll actually set this equal, so I can actually get rid of this. I'll set this equal to the rectifying line. So the equation for that is r over r plus 1 x plus 1 over r plus 1 times x sub d. So if x equals x sub d, it's r plus 1 over r plus 1 x sub d, y equals x sub d. That makes sense. So now what I'll do is I'll gather my like terms on one side. So q over q minus 1 minus r over r plus 1 times x equals 1 over q minus 1 z plus 1 over r plus 1 xd. And then finally, we just divide over. So x equals 1 over q minus 1. So write it like this. How's that? Z over q minus 1 plus xd over r plus 1. And that is all over q over q minus 1 minus r over r plus 1. So now that is the equation that will help us find the intersecting point of all three of those operating lines. And now what we can actually end up doing with all of these derivations is we can then actually define a set view operating set points for a distillation column and be able to calculate and graph out an entire McCabe-Thiele diagram, which is something that we'll do in the next video.